My name is Brody Wilzine, and I will be presenting my senior capstone project for ocean engineering projects and design. My project's name is Burn Wire Trigger for Recovery of Lost Underwater Assets. And I will go a little bit into the motivation behind my project. So, when at sea, sometimes lost sea objects can get stuck at the bottom of the sea, like the IR-3 in mud.
Yeah, don't mention it.
So when these objects get lost, oftentimes you'll have to manually recover them. This could either be through another drone, or it could be through other means like a winch or I don't know, anything really. There's a lot of ways you can do it. One way I wanted to do it is by releasing a gas to capturing a pressurized gas to increase the buoyancy of the object itself. So basically a failsafe for the object. The main way I wanted to accomplish this is by melting a string that would hold a system in tension that would, once released, puncture a CO2 cartridge. And that was the original goal for my project. So for a little demonstration of this original idea, stage one, it would be the object at the bottom of the seabed, and at first stage would just be to await the release. Once it gets the signal, then it would release and puncture the CO2 cartridge, inflating a balloon, and start to float. And this would once it reaches the surface, it would remain filled and then wait for recovery. And so then the original idea was to just have a signal pop out, and then it would be recovered. And then this is one way, the original idea that I had for my project. To begin with, I started off with feasibility of how much could this be applicable to how effective it could be, and using a MATLAB script and ideal gas law, I found that the maximum volume that a 16 gram CO2 cartridge could expand at the surface and all the way down to 600 meters is, at the surface, it's about 8.7 liters, and then down to about 100 meters, it's a little less. It's about a little less than 1 liter, about at 0.8 liters, and after that point, it's pretty much diminishing returns, where at some point you basically just can't expand anymore, and you can't lift your object anymore. So at about 100 meters, you get about 8 newtons of lift, or 1.8 pounds of lift, or buoyancy. And here's another slide with a more detailed, a more zoomed in version between 0 and 200 meters, where you can see the different ranges between going between in increments of 10 meters between 0 and 100 of how that changes between in the expanded gas that when you release the CO2 cartridge. And so at the surface, you'll have about 87 newtons of lift or buoyancy, and then it decreases all the way down to 100 at 8 newtons. So after this point, it's not much worth it. You might want to invest into other systems. So I wanted to focus on where that would be in my project. And then after that, I had to decide between a few different methods. I came up with 5 different methods. This would be using a solenoid, melting the string itself, using a motor, or also just releasing the gas itself, just completely avoiding a puncturing mechanism and just having it pre-punctured. I also researched a gunpowder method, which would just ignite gunpowder and puncture the CO2 cartridge outlet. And I rated them based on cost, complexity, reusability, durability, and reliability. And among these different methods, I found that the burn wire was the most optimum, mainly because of the low cost and low complexity. I found at the time that it had a medium reusability. That was because you could basically use a disposable small mechanism within the larger release mechanism, and you could just replace that rather than dispose the whole thing. That has a medium durability. Basically, you just use it once, and it doesn't need to be used very much. Once it's used, you just need to rearm it, and then it's good to go. And then the reliability is pretty high, since when things are not moving at all, they don't really have a chance there for failure. So before I get into the mechanics of what I needed to learn for the release mechanism, I need to introduce Ohm's law and power. So Ohm's law states that voltage is equal to the current times the resistance. So the potential difference, the electric potential voltage, is equal to the flow of charge, current, times the electrical resistance of the circuit. And this is true for all electricity, which is why it's a law. The power dissipated in a wire is the current times the voltage. Or, using Ohm's law, you could also say that the current squared times the resistance is equal to power. Where current in I for the unit, current I is amps, voltage V is in volts, resistance R is ohms, with the unit, the symbol sigma as the unit, and power in watts. The next one we have to learn is convection. This is where heat is transferred between a surface and a moving fluid. The thermal convective power loss is given by the equation Q is equal to H times the exposed surface area times the difference in temperature, where Q is power loss, H is the convective heat coefficient, the AS is the surface area exposed to the liquid, and delta T is the temperature difference between the material surface and the liquid temperature far from the surface. This is also known as T infinity, or ambient temperature, where the temperature measured far from the liquid. Okay, after this, I know Fusion has some thermal simulation, so I decided to do some thermal simulations and learn how to do that. I started off with a simple wire and adding a power to the wire, and this allowed me to estimate the amount of heat that would be generated in it. And it came out at 265 Celsius for this one. And it got a little bit more complicated. I estimated more with some more success, and it got even more complicated, which didn't help me out very much. It got too complicated to where I couldn't trust the values. So I tried to simplify it more, and I still couldn't completely trust the values because the geometry of this is just way too complicated. So I decided to, 1, learn more, and 2, try to simplify it a lot more. So the next thing I learned was the boiling curve. So in 1934, Nishiyama did an experiment where he tried to describe the different regimes of boiling. And he found that there are 4 regimes of boiling. That would be free convection, nucleate, transition, and film. Each of these having different properties. So in free convection, it's a rather constant increase in heat flux. Once you get past the end of free convection at point A, you get into the nucleate boiling regime. This is where between A and B, the heat flux rapidly increases, and then between B and C, it still increases, but not quite as much until you reach the point C, the critical heat flux point. This is a very important engineering point. This is where the stream starts to become enveloped in steam, and since steam is more insulative than water, it rapidly decreases the heat flux into the surrounding environment. If your system is power controlled, this means that your system will rapidly heat up, and it will heat up a lot. It will go from about 130 Celsius, which 100 in the graph it shows 30, but it's 130 Celsius because it shows the change in excess temperature, which is the the temperature of the surface minus the saturation temperature. The saturation temperature is the boiling point of water. So once it gets up to around 130 Celsius, it reaches the critical heat flux point, and then past this point, it rapidly jumps straight to E, which is over 1,000 degrees centigrade. This is often enough to melt most metals and poses a really intense problem for my project because it could destroy the project when I need to melt the wire, the stream. Because my stream has a melting temperature of around 270 degrees Celsius, which is much higher than 130 degrees Celsius. But the temperature that it will increase once I pass the 130 is way past anything my system can handle. So I need to add some insulation. But before I talk about that, I need to show you the experiment I did with it. So here you can see I have a wire between 2 bolts, and I put a positive and negative lead to either side. Let me play the video. Here you can see where I was able to reach this critical heat flux point, and you can see the flash there. That is where it goes from the critical heat flux point, it enters a transition, goes down to the Leidenfrost point, which is where it's completely covered in steam, and rapidly heats up to over 1,000 degrees C, which is why you see the flash. The flash is light being ejected from the very, very excited and hot material. It's pretty cool. So, after this, I decided I needed to start modeling this part and figure out what kind of insulation I wanted to do. I thought I could use injection molding to add the insulation, as this would be the most conducive to prototyping, because most other methods of adding insulation require heavy machinery. So my initial product went through 3 different iterations, which I will go through in the next few slides. The first iteration, it had just the main components of an injection mold. It had a cavity, it had a nozzle insert, it had air vents to allow the silicone to spread even, so that once the silicone is entered into the cavity, it can displace the air, and the air can leave through the air vents. Otherwise, you just get pushing the air against the cavity, and then there would be it wouldn't fill the cavity. It also had holes for the resistor leads, and it also had a string for the hole here, indicated by the 2 dotted circles. It also had bolts as well to keep the mold together while it cures. And next, I will go into the second iteration of the model. The second iteration of the model added quite a bit. It enlarged the air vents. It added way more points to pry the mold apart. It also added a few more bolt holes around parts where it needed, where it lacked the pressure before. And it also added countersunk holes to allow the part to fully thread the bolts all the way through. The last iteration did not have, it had too much length. So the bolts I could not use until this iteration. And then I figured out after the molding that underneath the resistor, just opposite side of the nozzle, there would be troubles with filling the gap because the air there couldn't escape. So to remedy this, I added another vent and displaced the single hole from the last slide into 2 different holes. And this kept pressure in this area while also allowing for an air gap there. And this would massively improve the mold quality and would allow me to finish my product. Now I'll show you some of the evolutions. So between these molds, I had to experiment with the mold release agent. Because silicone can stick to a lot of things, including PETG, which I used to 3D print this material, this model. The first one I used WD-40. WD-40 is not good for silicone because these sulfates in it inhibit the curing, and also the surface tension of it leads to it not to spread about the surface. It'll end up pooling, and this is not good for a mold where you need even coverage. The second one, I used soap, mainly the soap in the bathroom just adjacent to the lab. So that one worked good, but it's still stuck in areas, and this is, I think, likely due to the bathroom soap aerating the soap as it releases it. So it couldn't completely cover the surface as it was basically just super foamy. And then these last two, I used, this third to last one, I got a mold release spray from the internet, ordered through Amazon. And it had a little bit of an issue, but it was pretty much about the same release quality as this one, except near the top, I think because I sprayed way too much on it, I think it pulled, like, because the mold was sitting down with gravity. So the mold sits top here and bottom here, and because of gravity, it probably pulled the spray down because I sprayed too much, and this would cause it to pull up and then fall due to gravity. And so I think that's why it stuck near the top here when I tried to use the spray. I used too much, and then it pulled itself down due to gravity. And this last one, I used just dish soap. So I used dish soap, and I used a paintbrush, and I just dipped the paintbrush in the soap, and then applied the soap to the mold. And it came out perfect. This is also when I got the clear RTV silicone, and it looks pretty nice. So you can see the resistor in here, and also the string coming out either side. And this is where the bottom vent is. You can see it acting pretty well, where the silicone displaces it outside, and also these enlarged vents. And it creates a unique image. All right, so the final product is a clear insulated resistor that has a string wrapped around it. It's pretty simple, but the methods to get there were a little complicated at times. So I'm happy where this ended up. So before I need to test it, I need to estimate the amount of heat loss that will happen when I heat this up. So first we'll need to learn about thermal conduction. So thermal conduction is where heat energy moves through a stationary material. The thermal conductive power loss in cylindrical coordinates is given by the equation right there, where it says where Q, heat loss, is equal to the ratio between 2 times pi times the thermal conductivity times the length of the cylinder times the temperature difference, all over the natural log between the ratio of the outer radius and the inner radius. And this would allow me to go into the next topic, where we go into thermal circuits. So now that we know convective and conductive, we know the two different areas of our system. Because first we have our wire, which is our first layer. Then we have our insulation, which is the second layer. This is conduction from the wire into the insulation, and then we have convection from the insulation into the water. And so using this, we can equate the heat loss to electrical circuits, where a flow of current can be equated to a flow of temperature. So like in Ohm's law, where voltage is equal to IR, you can say that current is equal to a difference in electric potential over the electric resistance. And this can be equated in thermodynamics with a difference in temperature over a thermal resistance. And so the next step in this is to apply it. So we need to find the conductive resistance. So, and then because we know the difference in temperature, and so we need to find the power loss. So we need to find, once we get the thermal resistance, we can find the power loss. So the conductive resistance, we just use that equation we found on the slide before, and we end up with the resistance of the conductive power loss is equal to the difference in temperature over the heat loss due to conduction. And so basically, where you saw before where it was 2 pi k L delta T over Ln, it's basically just the inverse of that. And it's also the same for convective resistance, where you saw before I showed the model where it was HAS delta T. It's basically the inverse of that. So then we can add these two up and get the total thermal resistance. And then this can be inputted back into this equation to get the power loss. And so using the values of delta T is equal to 270 C, which is the melting point I need to get this thing at, minus 20 C, which is the ambient temperature of the water, and then we need the outer and inner radiuses, which is about 4.615 millimeters for the outer edge of the insulation. The resistor has about a radius of 1 millimeter, and the thermal conductivity of the insulation I chose is roughly 0.2 watts per millimeters C. The length of the resistor is about 5.16 milliliters, and the surface area is about 149 millimeters, 149.6 millimeters. So I assumed that the convective heat loss would be at the edge of nuclear boiling, just because it's a value known, and I can use that and see if there's any error in it. And then we can input all those into the convective heat loss equation. And for the dimensions in the model shown before, I have found that the heat loss for this circuit for water is 1.05 watts. And once I did a similar calculation for air and found that the expected power loss would be about 5 watts. And in the video,
I'm going to start increasing it by, nope.
So that was around 11 watts, or 11 volts is when it topped, which is around, once you use Ohm's law, is around 1 watt when it actually released. This is about 100% error, but considering that it's well below order of magnitude increase it's within the same order of magnitude, I think this is a pretty good test. And then I tried another one within water, pretty much similar thing, except where it has a vise hooked up to a weight below, it's weighted to the bottom of the water, where the weight is hooked over the top of the aquarium and let it hang over the other side. And so this one was captured in slow-mo, and it released at around 17 volts or 2.41 watts with a percent error of 141%, which is a lot more than when I tested it in water. When I tested it in water, it was well above 100 watts power draw. So, a few orders of magnitude less than what I had tested for. So I think this is a pretty large success, and I think this is pretty good. The cost of this item is, so some of the items I used in testing were WD-40. This turned out to be not good, but I used it anyway. Permatex Ultra Blue Gasket Maker. That's about $8.99. APEL Mold Release Spray was about $12.99. So for the total research and testing budget, it was around $30.97. The items used in the final product I used were, I used a tube of clear RTV gas sealant. This was by Abro. I used about 8 resistors, which were about 5 cents a piece. I bought some soap from Dollar Tree. This was $1.25, and some monofilament fishing line from Walmart, which was about $2.50. So total about $11.63 for all of the parts to make what I've made so far. And then, so this ends up with about a unit cost of about $1. It could be more, it could be less. It's a rough estimate. So the total project cost is about $42.60, which is pretty cheap for projects anyway. So there are a few things that I could have done differently. I went down a lot of rabbit holes. This led me to get progress done in very short leaps, and then taking a few steps back, and then leaping a few more times. So one thing I could have done better is communicating with Giro more and organizing what I needed to be done for the next week. Another thing I could have done better is experiment with more materials. This wasn't done to its full extent because of time and budget restraints, but if I had more time and budget, I would have experimented with more materials and tested out a few more combinations for release sealants and silicones. Another thing I wanted to do but couldn't really is more detailed calculations to reduce the error. I like that it was within an order of magnitude, but I'd like to get it with under 100% error. So that's one thing that I could have done better if I put more time into the actual calculations rather than other things in rabbit holes. Another thing I could have done better is better time management. Oftentimes I had struggles doing things at the last minute. It's not a thing you need to be doing. It's not conducive to a good work ethic, so that's something I need to improve upon. Conclusion, a small, cheap, effective product to melt the string underwater was created. Some technical skills I gained from this project were CAD, thermodynamics, fluid mechanics, 3D printing, injection molding, and knots. Some soft skills I learned were problem solving, just trying to figure out what was causing the issues with some of the molds, deciphering and how to solve them. Another one was time management. I got slightly better towards the end, but it was a little too too late. But I ended up getting my project finished, so I guess it all came together in the end. Another thing I learned was critical thinking, just trying to analyze complicated systems and learning how they could be calculated and or simplified, which came huge in my project. Some unexpected difficulty, there is no thermodynamics class in the USM course at the moment, hopefully in the future. But that was an unexpected thing I had to learn.
You're welcome to come back as an adjunct professor and teach it.
Another one is I had a difficulty learning proper way to calculate and simulating heat loss. I thought it would have been a lot more straightforward. It was a lot harder to find the method of thermal resistance than I thought it would be. And then once I found it, it was like, click. It's pretty simple. Some of the next steps in my project would be to optimize the amount of insulation needed. I kind of just assumed an insulation amount I needed, and further steps would be to optimize this amount to use as little or maybe more so that you could reduce the power that you need. Another way is to find or create an implementation for this device. This could be like my original idea, where you would puncture a CO2 cartridge to recover a device. But honestly, this could be applied anywhere where you need to release a system that's held in tension. Any questions? Yeah, around like slide 5, there's going to be a huge jump in quality.
The back end's much better. So, if you were to go on, have you done any brainstorming on what you would want to implement this in? Like,
I kind of wanted to do the original idea, but that would have to involve an already existing ABB, because I don't think I can make this small enough to where I could attach it to something. Maybe like, I don't know, something large like an ABB, but it would mess up with the drag and whatnot, so I'd have to, that'd be a little tricky to implement on the outside of something. If it's something like an object you don't want to lose, like, I don't know, a crate that's just really heavy, maybe you could add like, I don't know, multiple CO2 cartridges on the outside, or just have like a few really large ones where multiple of these systems activate once release it and it triggers. And so you saw where it's like about two pounds at around 100 meters. If it releases a lot sooner, it'll be more like 20 pounds. So just for a 16 gram cartridge. So it could be a lot more effective if you trigger it well before that 100 meter mark.
So when you're mentioning simulations earlier in the presentation, what makes you believe, or what made you believe that you couldn't trust it, and why? Why did you stop? I guess.
It's mainly because I didn't know what convective heat transfer coefficient to use, and at the time I was still learning it a lot. And once I started diving into it, it got into some pretty advanced graduate level mathematics. So I decided that since I don't know enough about convective heat transfer coefficients, I don't think I can trust my own assumed convective values that I inputted into there. And so the system may have been doing correctly, but I was not doing correctly when I was using the system.
Do you think it was a good rabbit hole that you went down, or do you think it hurt your time in the end?
I feel like it was a good learning experience, but the amount of time I spent on it probably could have been less than what I actually spent on it. Learning about, I mean, the simulations got me into learning about the boiling curve and the boiling crisis, so I wouldn't say it was a total waste. I would say it was a net positive for the project.
Yeah, I would agree with the statement. Often if you try to simulate something, even though it doesn't work out, you have to think about it and you learn usually quite a bit. So just
It
because
also-
ultimately you don't use it, it's not a waste of time.
Also allowed me to rethink about how to simplify it, where basically you got a tube and a tube.
So if somebody would come along and look at your path, say, maybe a weekend project, why did it take you a year? What would you tell him or her?
Yeah, it would probably be mainly due to the math behind it, but largely due to my time management for the project and the fact that I started from one angle where I wanted to make a complete product to throughout one semester where I kind of did try to do that, to where the second semester where I just shifted to just trying to do the cutting the string part. So that kind of held me back in getting a nice cohesive timeline through where I was working on just one idea, where it got separated into two.
But the answer you should have given is that the best engineering solution look awfully simple. And that's always the case. A good solution, it looks like, what the heck, obvious, that's how you do it. But to get to this point where it's obvious and super simple and works, it actually is quite time consuming. So I think you have a very good outcome actually.
Does the same go for presentation lengths? That's engineering presentations only 12 minutes long.
Brody had 33 minutes, so
I give him extra time.
yeah, exactly, he took your time.
I really liked how you went into the theory behind it and didn't just say, I did some math and here's the product. You actually like explain the theories. I don't necessarily have a question, I just wanted to say that you did good.
Yeah, I really did like how you put the chart with the boiling point and then the video right after proving the theory behind it.
It was kind of the goal I wanted to do, because I couldn't find many videos where they had many stats behind their things. And I kind of want to upload that and add some more information about how I tested it and whatnot. Because most of the videos I found where they did stuff like that, there was no information, there was no description, just the name, basically, hey, it's just string underwater, and that was pretty much it. And it wasn't very helpful to me. So I don't think I could provide enough detail to where I would have liked the detail, but I could provide enough detail to where it's better than nothing.
You're explaining why it works, not necessarily just the fact that it works.
Yes.
Yeah, very good. Any other questions?